Modules and homological algebra, lecture 14, natural transformations. We start with the definition of a natural transformation. Let C and D be two categories. Let F and G be two functors from C to D. Definition: a natural transformation eta from F to G is a collection of morphisms in D which are indexed by objects in C. So for each object I in C, we have a morphism eta I in D from the object f of I to the object g of I. And this collection of morphisms should satisfy the following requirement. For any morphism h in C from I to j, we should have that the composition of g of h after eta I should be equal to the composition of eta j after f of h. In other words, the following diagram should commute. So we have a diagram with four objects, f of I, f of j, g of I, and g of j. We have the morphism f of h from f of I to f of j. We have the morphism g of h from g of I to g of j. And then we have the morphisms eta I from f of I to g of I. This is a part of our natural transformation. And we have the morphism eta j from f of j to g of j. This is also a part of our natural transformation. So this square should commute. So g of h after eta I, this path, should coincide with the path eta j after f of h. This is this path. Here are some examples. The first example is a trivial example. If we take f to be equal to g, then we have the identity natural transformation, the identity on f. And this natural transformation is given by the collection of identity morphisms in D from f of I to f of I. Each such set in D has the identity morphism, and we take it as a part of this transformation. And then the axiom that f of h after the identity on f of I is equal to identity on f of j after f of h. That's trivial because both sides are equal to f of h. Example 2. So let C be a category and I and j two objects in C. Then we have the corresponding representable functors Ci blank and Cj blank. So we take the functor of taking all morphisms in C which start at I and then end in some object, which is the variable of the functor. And we can take all morphisms in C which start with j and they end at some fixed object, which is a variable of a functor. So these are two functors from C to the category of sets. Now, for a fixed morphism f in C from j to I, we have the natural transformation of recomposition with f. So we start with f and then compose it with some morphism. And this will be a natural transformation from the functor Ci blank to the functor Cj blank. So indeed, if we have a morphism in C from I to k, let's call this morphism h, then we can compose h after f because f terminates at I, and we have a morphism in C from j to k because f starts in j. So this thing defines a map from the set Cik to the set Cjk. Moreover, for any morphism g in C from k to m, we have that the composition of g after composing something after f. So we can put here the brackets in two different ways because this composition is associative. Then this associativity, this is exactly the axiom for the natural transformation. So this g after something, so this is the value of our functor at the morphism g, and here precomposing with f, this is we are doing our natural transformation. And on the other side, we first apply the functor, and then we precompose with the natural transformation. So this is the axiom of the natural transformation, which implies that precomposition with f is indeed a natural transformation from this representative functor Ci blank to the representative functor Cj blank. Note that f goes from j to I, while we get a natural transformation from Ci blank to Cj blank. Next, let us discuss composition of natural transformations. So natural transformations can be composed. Let C and D be two categories. Let F, G, and H be three functors from C to D. Let eta be a natural transformation from F to G, and zeta be a natural transformation from G to H. Then, for any object I in C, we can consider the morphism, which is the composition of zeta I after eta I. And this is a morphism in D from f of I to h of I. And we denote this morphism as zeta composition with eta evaluated at I. So here is a picture. Eta I by definition is a morphism from f of I to g of I, and zeta I is a morphism from g of I to h of I. So we compose them and get zeta I after eta I, and we just denote it as the evaluation at I of zeta after eta. And we claim that this zeta after eta, this collection of morphisms, is in fact a natural transformation from the functor f to the functor h. So here is a proof. We consider the following diagram. So we have f of I, and then eta I, which goes to g of I, and then zeta I, which goes to h of I. And we have f of j, eta j goes to g of j, and zeta j goes to h of j. And then we have a morphism r in C from I to j. So then we have f of I, and then f of r, which goes to f of j. Similarly, g of r, which goes from g of I to g of j, and h of r, which goes from h of I to h of j. So in this diagram, the first square commutes because eta is a natural transformation from f to g. And the second square commutes because zeta is a natural transformation from g to h. But then the whole diagram commutes. In particular, the two paths on the perimeter of the diagram, they commute. And this means exactly that zeta after eta is a natural transformation from f to h, and completes the proof of our claim. We record the following properties of the composition of natural transformations. First of all, this composition is associative. That is, if we have four functors f, g, h, and k from C to D, and three natural transformations, eta from f to g, zeta from g to h, and xi from h to k, then we can compose xi after zeta after eta, and of course we can put the brackets in two different ways. So the claim is it doesn't matter in which ways we put the bracket, we get the same result. So xi after zeta and then after eta is equal to xi after zeta after eta. So the composition of natural transformations is an associative operation. Next, composition of natural transformations is also a unital operation. That is, for any natural transformation eta from f to g, we can compose eta with the identity on g after eta or with the identity on f before eta. In both cases, the outcome will be equal to eta, because the identity natural transformations on any functor, they are given by the identity morphisms on the corresponding objects. We can summarize it in the following fact. Let C and D be two categories. Then, the associativity and unitality of the composition of natural transformation implies that we have the category of all functors from C to D, whose objects are functors from C to D, whose morphisms are natural transformation of functors, where composition is just composition of natural transformations, and the identity morphisms are the identity natural transformations. So we can now speak about the category of all functors from a fixed category C to a fixed category D. And one immediate consequence of this is that we have a well-defined notion of isomorphism of functors. Two functors f and g from C to D are isomorphic, provided that they are isomorphic as objects in this category of functors. We can spell it out what it means. So in other words, two functors f and g from C to D are isomorphic if and only if there are natural transformations eta from f to g and zeta from g to f, such that the composition of eta after zeta equals the identity natural transformation on g, and the composition of zeta after eta equals the identity natural transformation on f. Here is an example. Let R be a ring. Consider the category of all left R modules, which is usually denoted by R mod with capital M. Then, of course, there is the identity functor in this category, and there is another endofunctor of this category given by tensoring with the ring R over R. And the claim is that these two functors are isomorphic. In order to prove that they are isomorphic, we construct the natural transformations in both directions, from tensoring with R to the identity and back. The natural transformation eta from the functor of tensoring with R over R to the identity is given by the following morphisms. So for each object M in the category R mod, we have a homomorphism from the R module R tensor over Rm to M, which is given by sending the element R tensor M in the sphere space to Rm. It is easy to check that this is a homomorphism of R modules and that this defines a natural transformation from the first functor to the second functor. In the opposite direction, we have the natural transformation zeta, so from the identity to the functor of tensoring with R over R, which is defined by the following morphisms. So we start from an R module M and then send it to R tensor over Rm by sending an element little m in M to the element 1 tensor M in this tensor product. So the composition zeta after eta sends R tensor M to 1 tensor Rm by definition, but since our tensor product is over R, this is equal to R tensor M. And the composition of eta after zeta sends M to 1 times M, and this is equal to M by the action axioms. So this shows that the composition of these natural transformations in both directions give us the identity natural transformation on the corresponding functor, which indeed shows that the functor of tensoring with R over R is isomorphic to the identity functor on the category of all R modules. This we now can use to define the notion of equivalence of categories. Recall, two categories C and D are isomorphic, provided that there are functors f from C to D and g from D to C, such that the composition of f after g is equal to the identity functor on D, and the composition of g after f is equal to the identity functor on C. So now we make the following weaker definition. We define the weaker notion of equivalence of categories. Definition: two categories C and D are equivalent, provided that there are functors f from C to D and g from D to C, such that the composition of f after g is isomorphic to the identity functor on D, and the composition of g after f is isomorphic to the identity functor on C. Such functors f and g are usually called quasi-inverses of each other. Quite often one says simply inverses, but it is a bit more correct to say quasi-inverses. So what we have done, we have taken a very strong condition of equality of functors and substituted it by a weaker condition of isomorphism of functors. And the motivation for that is that equality of functors is very difficult to produce in reality, especially in the situation when we work with categories whose objects do not form a set. And to produce and check isomorphism of functors is much more realistic. So on the module category, it's very difficult to ensure that some functor is the identity on the module category. But as we saw in the previous example, tensoring with R over R is isomorphic to the identity functor. It is not the identity functor, but it is isomorphic to the identity functor, and this is what is typically much easier to do in real life. Here is an example. Let's see be the category with one object I and one morphism, the identity on I. So we have one object and one morphism. And of course, identity on I composed with identity on I is identity on I. Let D be the category with two objects, J and K, and four morphisms. The morphism 1J from J to J, the morphism 1K from K to K, the morphism alpha from J to K, and the morphism beta from K to J. Since all local morphism sets are singletons, composition is just uniquely defined. So if we compose 1J after 1J, we get 1J. We cannot compose 1J after 1K or 1J after alpha. Composing 1J after beta gives us beta. Similarly, 1K can only be composed after 1K, producing 1K, and after alpha, producing alpha. Alpha can be composed after 1J, giving alpha, and after beta, producing 1K. And finally, beta can be composed only after 1K, giving beta, and after alpha, given 1J. Note that these two categories have absolutely no chance to be isomorphic because the first one has one object and the second one has two objects. If you have an isomorphism on categories, then such an isomorphism induces a bijection on objects. And here there is no chance to have a bijection because the sets of objects have different cardinality. So these categories cannot be isomorphic. So we will show that these categories are, in fact, equivalent. For this, we define two quasi-inverse equivalences between these categories. We define the functor f from C to D by sending the object I to the object J and the morphism 1I to the morphism 1J. Define the functor G from D to C by sending both objects J and K to I and all morphisms 1J, 1K, alpha, and beta to 1I. It's easy to check that these F and G, they are indeed functors. Of course, directly from the definition, applying G after F produces the identity on C, simply because there are no other functors on C, just the identity on C. And clearly, F after G is not the identity on D because the objects J and K collapse to the same object J. But we claim that F after G is isomorphic to the identity on D. And in order to prove that, we need to construct natural transformations eta from F after G to the identity on D and zeta from the identity on D to F after G, such that these two natural transformations are each other's inverses. So their composition gives the identity on the corresponding functors. Again, since all local morphism sets are singletons, we do not really have much choice. So note that F after G sends object J to J and object K to J, while the identity, of course, sends J to J and K to K. So we define the natural transformation eta evaluated at the object J as the unique morphism from J to J, which is 1J. And we define eta evaluated at K as the unique object from J to K, which is alpha. Similarly, we define zeta evaluated at J as the unique morphism from J to J, which is 1J. And we define zeta evaluated at K. There should be a morphism from this K to this J, and there is a unique one, which is beta. So there is only one choice for our definition. That these are natural transformations, this follows directly from the fact that local morphism spaces are singletons. If you write the diagrams, the axioms for the natural transformation, they obviously commute because there is only one morphism from any object to any other object. The two passes on this diagram give one morphism because there is only one. And similarly, the fact that the composition of these two natural transformations is the identity natural transformation in both orders. This follows directly from the fact that the local morphism spaces are singletons. Consequence, we have just proved that F and G are mutually quasi-inverse equivalences of categories between the category C and the category D. So we have two categories which are not isomorphic, but which are equivalent. The main result of this lecture is the following characterization of equivalences of categories. Theorem. Let C and D be two categories. Let F be a functor from C to D. Then F is an equivalence of categories if and only if the functor F is full, which means that it is locally surjective on morphisms. It should be also faithful, which means that it is locally injective on morphisms. And it should be dense. Alternatively, this is called essentially surjective. This means that the image of this functor hits all isomorphism classes of objects. Let us start the proof of this theorem by proving necessity. Let F from C to D be an equivalence with quasi-inverse G from D to C. Let eta from F after G to the identity on D and zeta from G after F to the identity on C be invertible natural transformations. Then, for any object I in D, we have that eta I from F of G of I to I, this is an isomorphism. In particular, F of G of I is isomorphic to I, which means that F is a dense functor. For each object I, there is an object in the image of F which is isomorphic to this object I. Well, since G is also an equivalence, we have also just proved that G is dense. Any equivalence is a dense functor. Further, for any pair of objects I and J in D, the map, when we take some morphism, recompose it with eta I and postcompose with eta J inverse, this is an isomorphism between Dij and F of J of Dij. And of course, exactly the same map is an isomorphism between Dij and D from F of J of I to F of J of J. So this means that the letter space D from F of J of I to F of J of J is isomorphic to F of J of Dij. And since the functor J is dense, so G of I and G of J runs through all isomorphism classes of objects, it follows that the functor F should be full. So F applied to something gives us the whole morphism set. And here F of G of I and F of G of J can be arbitrary. So we have just established that any equivalence is full. In particular, G is also a full functor. So it remains to prove that any equivalence is faithful. So assume that something maybe is not faithful. Assume that we have two morphisms H and R in C from K to M, which ascend by F to the same thing. So F of H is equal to F of R. Since G is a dense functor, we may assume that K is actually equal to G of I and M is equal to G of J. As G is a full functor, we then may assume that H is equal to G applied to some H tilde, and R is equal to G applied to some R tilde. And then we have the equality that F of G of H tilde is equal to F of G of R tilde. But we have already seen that recomposing with eta I and postcomposing with eta J inverse is an isomorphism between F of G of Dij and Dij. And here we apply F of G exactly here, and we end up in Dij. Since this map is an isomorphism, it follows that H tilde is equal to R tilde. In particular, G of H tilde is equal to G of R tilde, and this means this should be R tilde. And this means that the functor F is full. And this completes the proof of necessity. Now let us prove sufficiency. Let F from C to D be a full, faithful, and dense functor. So we want to construct a quasi-inverse G from D to C. So in each isomorphism class of objects in D, we fix one object, which is of the form f of I, where I is some object in C. We can do that because f is dense. So it hits all isomorphism classes of objects. Now for any object J in D, which is isomorphic to this fixed f of I, we fix an isomorphism alpha J from J to f of I. So we have done now many choices. We fixed an object in each isomorphism class, and for each object isomorphic to this fixed object, we fixed an isomorphism between them. So now we define G. So we set G of J to be equal to I under this assumption. Next, we know that F is full and faithful. So F is a bijection from C I1, I2 to D f of I1, f of I2. Therefore, for any morphism H in D from J1 to J2, we can define G of H as F inverse applied to the following morphism: alpha J2 composed with H composed with alpha J1 inverse. We know that this morphism which we have here, by definition, it is a morphism from f of I1 to f of I2. And therefore, we can apply F inverse because F is a bijection between these two sets. So in other words, what we do, we collapse each isomorphism class of objects in D to the object F of I, and on these objects we define the functor G as the inverse of the functor F. Now we have only one morphism, which is in the image of F, so we define G as the inverse. Okay, so this is a definition of G, and let us show that G is a well-defined functor. So assume that we have two morphisms, H from J1 to J2 and R from J2 to J3. Then R after H is a morphism from J1 to J3. By definition, our G of H is equal to F inverse to alpha J2 after H after alpha J1 inverse. Similarly, G of R is F inverse applied to alpha J3 after R after alpha J2 inverse. And G applied to R after H is F inverse applied to alpha J3 after R after H after alpha J1 inverse. Since F is a functor, we have that F inverse applied to alpha J3 after R after alpha J2 inverse, composed with F inverse applied to alpha J2 after H after alpha J1 inverse is equal to F inverse applied to the composition of the arguments. And in this composition, we can cancel alpha J2 with alpha J2 inverse in the middle. And so F inverse applied to the long composition is equal to F inverse applied to this shortened composition, which is exactly the expression which we use to define G of R after H. This proves that G of R after H is equal to G of R after G of H. And similarly, one checks that G sends identity morphism to identity morphism. This follows directly from the definition. So we have now checked that G is a well-defined functor. Now we need to construct an invertible natural transformation eta from F after G to the identity on D. So we define eta evaluated at J as alpha J inverse. This is clearly invertible. Alpha J is invertible and alpha J inverse it's inverse, so alpha J inverse is also invertible. And to prove that this is a natural transformation, we need to check a certain diagram, which is an axiom for the natural transformation, and this diagram looks in our case as follows. So we have J1, J2, and H between them. This is the identity functor. So we apply F after G, so we have F of I1, F of I2. Then our natural transformation is given by alpha J1 inverse here and alpha J2 inverse here. And the functor G is given by F inverse applied to alpha J2 after H after alpha J1 inverse. And then we apply functor F, so we put one F here, then F and F inverse cancel each other, and we get a commutative diagram. So we have an invertible natural transformation. The inverse of this natural transformation is also a natural transformation. This is easy to check. And this shows that f after g is isomorphic to the identity functor on D. Well, and finally, we need to construct an invertible natural transformation zeta from G after F to the identity functor on C. Let us note that since F is full and faithful, it sends non-isomorphic objects to non-isomorphic objects. And also note that we have chosen a fixed I in each isomorphism class in C in our definition. So for each isomorphism class in G, we fix an object of the form f of I, so we have also fixed I in the corresponding preimage, the isomorphism class in C. So now if you have an object I tilde which is isomorphic to I, then we have the isomorphism beta I tilde, which is defined as f inverse of alpha f of I tilde from I tilde to I. So we define zeta I tilde as beta I tilde inverse, and this is clearly invertible. Similarly as on the previous slide, one checks that the zeta is a natural transformation and is an invertible natural transformation, which shows that G after F is isomorphic to the identity on C. And this completes the proof of our main theorem. Let us apply this theorem to the following example. Let C be the category of all finite-dimensional vector spaces over some field K and K-linear maps between them. So this is what is usually denoted by K mod with little m. Let D be the category defined as follows. The objects of D are non-negative integers. For two integers I and j, the morphisms from I to j are all matrices with j rows and I columns and coefficients in K. Composition is just the matrix multiplication, and identity morphisms are identity matrices. It's obvious that these categories are not isomorphic because D has countably many objects while C has uncountably many objects. However, we claim that these categories are equivalent. So in order to construct an equivalence, we use our theorem, so we construct a full, faithful, and dense functor from C to D. For this, we fix a basis in each vector space V. Let's call this basis E sub V. And now we define the functor f from C to D, which sends each vector space to its dimension, and the linear map between two vector spaces to the matrix of this linear map with respect to our chosen basis. Then, from the basic linear algebra, we know that this defines a functor. This means that if we compose linear maps, we then just multiply the corresponding matrices, and that this functor is full, faithful, and dense. It is dense because for any dimension there is a vector space of that dimension, and it is full and faithful because each linear map has a unique matrix, and that matrix defines the linear map uniquely if we have chosen the basis, as we did. And so, by our main theorem, this is an equivalence of categories. Some problems and questions at the end. Problem 1. For a ring R, check with all details that sending R tensor M to Rm defines a natural transformation from the functor of tensoring with R over R to the identity functor on R mod. Problem 2. Similarly, check that sending M to one tensor M defines a natural transformation from the identity functor to the functor of tensoring with R over R. Problem 3. Let eta from F to G be a natural transformation such that eta I is invertible for all I in C. Show that if we take the inverses of all eta i's, then this collection defines a natural transformation from G to F in the opposite direction, and that this natural transformation is actually the inverse of eta. Problem 4. Check with full details that the functor G considered in the proof of characterization theorem sends identities to identities. And finally, problem 5. In the proof of characterization theorem, check with full details that zeta is a natural transformation. Thank you very much and see you next time.